Hello, I'm your host, Khari Douglas, and welcome to Catalyzing Computing, the official podcast of the Computing Community Consortium. The Computing Community Consortium, or CCC for short, is a programmatic committee of the Computing Research Association. The mission of the CCC is to catalyze the computing research community and enable the pursuit of innovative, high-impact research. In this episode, I interview Dr. Nadya Bliss, a CCC council member and the executive director of Arizona State's Global Security Initiative. Before joining ASU in 2012, Bliss spent 10 years at MIT's Lincoln Laboratory, most recently as a founding group leader of the Computing and Analytics Group. In this episode, we discuss her time at Lincoln Lab, what a federally funded research and development center does, and the history of graph analytics. Enjoy! Today, via Zoom, we have CCC Council Member Nadya Bliss, Director of the Global Security Initiative at Arizona State University. Nadya, how are you doing today?
I am pretty good. How are you, Khari?
Doing well, all things considered. So let me ask you, where did you grow up and how did you first get involved with computer science?
So I was born in St. Petersburg, Russia, what is now St. Petersburg, Russia. At the time, it was Leningrad in the former USSR, so the Soviet Union doesn't exist anymore. I have always loved math. I was one of those little kids that didn't want to be a ballerina or a princess or a queen. I really wanted to be a mathematician. So from very, very young age, I just remember really, really loving math. And then when I was almost 13, so it was about 12 and a half, my family came to the US and I continued to love math, but I was a little bit concerned that I would need to spend too much time in school, and I really wanted to make sure I had a job when I graduated college. That was important. I had a ton of college loans, and I knew I was going to have a ton of college loans. I was obviously still in high school at the time. So I decided to try a computer programming course in high school and, took computer science AP classes in high school. Very fortunate. I had a really good math teacher that was also my computer science teacher. And there's some beautiful parallels between computer science and math that allowed me to kind of maintain my passion for both. And I realized that there are aspects of computer science that are basically mathematics. So that's how I got into it.
Okay, so in high school?
Yeah, I would say so. I would say, so I think, Soviet Union was a funny place. A lot of the technical education was very advanced. So I think I had some of the very basic programming classes back in fourth grade, back in the Soviet Union. But in terms of a career, I think I decided it was either 9th or 10th grade of high school in Ohio, public school in Ohio, Cleveland, Ohio, suburb of Cleveland, Ohio, that I would major in computer science in college. And I realize it's really weird. A lot of 9th and 10th graders have not picked their majors, but I am that person that has been planning everything pretty much since I was 6.
Yeah, that does seem pretty early. So how old were you when you moved from the Soviet Union to the United States?
I was 12 and a half when my family moved.
So did you notice, I mean, obviously there was some degree of culture shock, but in terms of like school and math and computer science, did you notice any differences when you moved?
Oh, so lots of differences. And it's a strange, 12 and a half is it's a funny age, right? Especially for us nerds. Like generally that time period is a little bit challenging, but then on top of it, if you add on like you're that foreign kid in class that is not necessarily totally fluent in the language, it's a little extra hard. So I'll tell kind of 2 little anecdotes. One is not really related to the technical side, but one of my early memories of when we moved to the US was the first time we went to like a basic American supermarket. Mm-hmm. And in the Soviet Union, and when the Soviet Union was falling apart during that time as well, you often had to stand in line for food. You had to stand in line for food. You had to kind of buy the food that was available that day. And I remember going to one of those supermarkets, and it was like, this feeling of just like light and all the aisles full of all this food, and it was just surreal. So it's not a very sophisticated memory, but there's something about this abundance and choice that just was surreal. As far as on the technical side, what I think was very interesting is I was taken aback by basically the negative connotation, especially as a teenage girl, that came associated with being good at math. In the Soviet Union, and again, I was in St. Petersburg, and I come from a family that's very highly educated, and my mom is an engineer, my grandma is an engineer, and my other grandma was a medical doctor. So it was sort of expected that you're good at math, and it didn't matter if you were a girl good at math, or who you were good at math. And I pretty much realized early on in high school that being good at math is not cool, and this is not going to be one of those movie or Saved by the Bell high school experiences, and I'm just going to put my head down and work through it. That was strange. I thought that was odd.
So prior to joining GSI, I know you spent a long time at MIT's Lincoln Laboratory. What is that? Could you talk a little bit about that?
Yeah. So Lincoln Laboratory, MIT Lincoln Laboratory, is a federally funded research and development center. So you sometimes hear people refer to it as an FFRDC. It's not the only FFRDC. There are other FFRDCs in the United States. So, for example, Sandia National Labs is an FFRDC. Oak Ridge National Laboratory is an FFRDC. So what's pretty special about Lincoln Laboratory is both it being formally part of MIT, Massachusetts Institute of Technology, the university, and also the fact that it is a prototyping national lab. So there's a number of FFRDCs that do analyses. Lincoln Laboratory actually builds things, like builds processors and prototypes and algorithms and technologies, and it doesn't produce them, but it builds these prototypes. And that's pretty cool. When you're sort of thinking about the type of things that you want to do, for someone like me, I really, really, really love research, but I also really wanted to have that research be connected to something tangible. So when I was graduating from Cornell with my master's, I applied very, very broadly. So I sent applications to companies in the financial sector, to just big companies that had IT departments, to Microsoft. Microsoft was another place I potentially considered going to. And Lincoln Laboratory to me was one of those places that really combined all the elements of research and application in this one place. And that's what I really loved about both selecting it as a place to go work and then spending 10 years there.
So could you explain a little bit more about what a FFRCD is?
FFRDC?
Yeah. For people who don't know,
Yeah, so essentially, Lincoln is a Department of Defense FFRDC. So it works very closely with Department of Defense on applying the most advanced concepts in specifically technology research to big Department of Defense problems. And there is this huge emphasis on technical rigor combined with a requirement for applicability to the mission of the Department of Defense. So, for example, an FFRDC like Lincoln Laboratory typically does not do basic research, but often it does early stage applied research and then applies it to the problems in the national security space. It is a technology FFRDC. So the mission of Lincoln Laboratory is technology in support of national security. So the vast majority of the technical staff there fall into the disciplines like electrical engineering, computer science, mathematics, and physics. So it's like this place that is just like full of nerds, and it's amazing.
And what's the difference between basic and applied research? I know I've heard the terms like 6.1 and 6.2 and 6.3. Could you explain those distinctions?
Yeah, so typically when people say basic research, it's usually very, very early stage research. And I would also like to distinguish between basic research that is curiosity driven and basic research that is application driven. So typically in that very, very early stages, you are just testing out basic concepts. So for example, in computer science, it may be a pseudocode for an algorithm or a set of equations to try out if you're, for example, working out in graph theory and looking at sparse matrices and how they apply in context of graph theory. And sometimes, so if it's curiosity driven, it could just be because, I want to try this out. I want to try to understand what is a projection of this type of matrix going to look like in a two-dimensional space. So it's just like you're just curious about what would happen. If it's application driven, you may be wanting to solve a particular problem, but it's still that in those very, very early stages. Once research becomes applied, typically there is a particular set of specifications that are coming that are informed by an application. So, for example, you may know the scale of the data that you're working with, so how many data points or the type of patterns you may be interested in identifying.
Okay, that makes sense. So could you talk a little bit about the kind of work that you did while you were at Lincoln Laboratory?
So when I left Lincoln Laboratory, I was the group leader of the computing and analytics group. And essentially we did a whole bunch of different computer science type of things. So we were one of the kind of major computer science group in the laboratory. I would say when I first started at the laboratory, there wasn't as much computer science. There was some, but it was very much an electrical engineering shop. And then by the time I left, I think there was a appreciation of computer science as a discipline as opposed to a support discipline, like developing software for an electrical engineering project. So the type of things that we did in my group were, for example, we worked on advanced computer architectures, so instruction set architectures, particularly for either novel applications like graph applications, graph theoretic application, network applications, or using emerging novel devices. So, for example, photonic interconnects as opposed to electronic interconnects. And we also had basically all of the high performance computing in the laboratory was under the oversight of the group that I ran. And a lot of my early work at Lincoln really focused on high performance computing. So basically, how do we take complex signal processing codes and map them onto multiprocessor architectures? A lot of that work was happening in the group. And then we had a pretty significant effort on all types of analytics, but the biggest one was on graph analytics. So analysis of networks, analysis of relationships between entities, and trying to see if there's emergence of patterns in those.
Okay. Well, we'll talk more about graph theory in a bit. In the prep for this, I know you said that you were the group leader for the computing and analytics group, and that Lincoln Labs high-performance computers were under your oversight. What's involved in doing oversight of an HPC?
Oh, it's really funny. One of the first times I thought, oh, wow, this is what a leadership position is like, was when, so we really thought about how do we essentially have green computing. So not just efficient computing, but efficient computing per power unit. So computing that uses minimum power. And at the time, one of the ways to implement it was using these containers. And I remember, so the location where these containers with high performance computing existed were somewhere by a river in Massachusetts. And I remember getting a call, I think it was like on the weekend, that the river had flooded. And I was thinking, what am I supposed to do when there is a container that's flooded? I mean, and there's lots of people that are involved that help you manage through that. But that's one of the examples, that's what's involved. But on a more serious note, I think what's interesting about high performance computing is just how it is both a resource and a research area at the same time. So we had amazing groups of people that, and I think, I mean, that effort now has spun out. And I think Lincoln Laboratory now has a high performance computing facility that's its own thing. And I believe Dr. Jeremy Kepner runs it. And I worked with Jeremy since when I first started at the lab. So you have a ton of amazing researchers doing sort of this very advanced early stage research on how to make the most efficient parallel and high performance computation. And then you also have a ton of brilliant technical people that work with the rest of the laboratory to help parallelize codes and make sure codes scale well and develop these systems that allow for minimum intervention of an individual when you have to rewrite a code. So it's this interesting balance that lives in between research and application. But then there's also flooding. So that's kind of a good example.
Yeah. So I don't know how involved you still are with the field, but...
Not very much.
Okay. Well, if you can speak to it, has it changed in any way since when you first got involved?
So the thing that I will say, and this is probably an artifact of just getting older, is one thing that I've been noticing is a lot of the really challenging problems persist. So for example, mapping codes onto computer architectures is not a solved problem and still is subject of theses for PhD students. I mean, that's a very interesting area. The other thing that I would say is, so when I first started at Lincoln Laboratory, I remember a lot of discussions about the slowing down of Moore's law. Essentially, the fact that we're taking for granted that computational speed is doubling about every year and a half, I think it is, which of course Moore's law is not about computational speed, but about the space, how many transistors you can put on a chip. But then, the effect of it is that it's been easier to get faster processors with essentially very little work on the programming side. And what's interesting, and just recently, I was in another meeting, and people are still talking about Moore's law. So there's both a ton of innovation, and then there are these persistent themes that stay. And if you're lucky enough to pick good problems, you can both make impact and then also see longevity of that research. So that I think, in many ways, high performance computing has changed drastically, because now we essentially have a high performance computer in our pocket because our iPhones are all high performance computers, and computational speed and just amount of time we can do both locally and remotely has drastically changed. But those big research questions like Moore's law and novel architectures and architectures with different memory access patterns and programming models for increasingly complex architectures, those problems, there's still things to work on in the community.
Of those problems, are there any that you personally find more interesting or you think apply more to topic areas that you're interested in?
For me, what I think is particularly interesting, so let's see, I would say I think the underlying processor architectures still have trouble with the shape of matrices that could be used to represent networks and graphs. And I think that's interesting. So if we go back, to sort of the beginning, how I got into this, ultimately, my passion has always been the algorithmic and mathematical aspects of computer science. I think hardware is brilliantly interesting, but it is where that coupling happens that, to me, I find personally most interesting. So I think when I worked on developing computer architectures for graph algorithms, that was the most interesting type of computer architecture and processing system work for me personally.
Okay, so you said the shape of a matrices. What do you mean by shape?
And I'm sorry, I probably shouldn't have said the shape. It was more the sparsity pattern. So if you think about let's say, traditional fluid mechanics type of codes. The sparse matrices, even if they're sparse, often have very kind of regular structure in them. So there's either dense rows or dense columns or dense not dense, but diagonals that are, filled out. And if you have a sparse matrix that's very structured from a computational perspective, you essentially end up having something that's you can almost optimize on as if it is a dense matrix. However, when you go to a sparse matrix derived from a network, like, for example, the type of social networks that Facebook or Twitter or whoever use, they do not look like those matrices at all. Some of them have power law structure, but there's this very, it's very irregular structures that you can't take advantage of. There's no dense blocks. And that's what I meant. So it's essentially the sparsity pattern. So if you essentially take your matrix and create a little square where you color in where the non-zeros are, it looks like just a weird random pattern. It's not actually random generally. It's not at all, but it looks very irregular and it's hard to take advantage of computationally from an optimization perspective, from a performance optimization perspective.
Okay, that makes sense. So this might be a good segue then. So what is graph analytics, which you said is one of the things you worked on? I know what your dissertation was about. And why is it important?
Graphs, so maybe we can start a little bit with just like, if it's okay, if I can say, what is a graph? So graph is essentially a mathematical abstraction or a mathematical construct that allows you to represent entities, which in graph theory I refer to as vertices, and relationships, which in graph theory I refer to as edges. And you can represent graphs as edge vertex pairs. So you essentially can encode like these two vertices are connected, so that makes an edge. These two vertices are connected, so it's essentially a set. Or you can represent graphs as an adjacency matrix, which essentially gives you that sparse matrix representation. You basically have rows and columns represent your vertices, your entities, and then there's a non-zero entry in the matrix if those two vertices are connected. So that's a graph. Basically an abstraction. And why graphs are important is, and of course, I'm going to sound like someone who likes graphs here. Almost anything can be represented as a graph. So things like, relationships between people, organizational structures, financial transactions, social media communication, Girl Scout troops are graphs. Your relationship between proteins, for example, are often studied as graphs. Roadways, transportation networks are graphs. And people use the word graph and network interchangeably. Network tends to be a more descriptive term, whereas the graph is like the formal mathematical definition. So I even think, and this is probably because I sort of loved this kind of stuff as a kid and I'm very much a nerd, I generally think of concepts as graphs, right? Like, so if I think about the brain and how things are interconnected, I'll be like, oh, this thing over there connects to this thing over there. And that essentially is a graph. The other thing that's really interesting about graphs is that it changes the distance between entities. So, for example, if you think about social networks, right, you have your geometric distance, which is in a two-dimensional space, but in graph space, you can be actually really close to someone in DC, even though you don't live close together at all, right? So there are these fundamental principles that they encode these relationships in these highly multi-dimensional way. Obviously internet is a graph. That's kind of an obvious one. So they're just everywhere. They're just everywhere. And to be honest, they're not that well understood. And the other thing that I think is really fascinating is as we've scaled into this world of connectivity, just the scale of graphs around us has changed. And I think that also creates some interesting space. I'm going to pause here because I feel like I could just go on and on and on about graphs.
No, so I was going to ask you about because you sent me your PowerPoint presentation from your dissertation,
Yes.
and it has a couple different examples of different graphs.
Yes.
The first one was something I read about prepping for this, the 7 bridges of Koningsberg problem, which I believe is sort of the original graph theory problem.
Yeah, so that's the other thing that's so cool about it, right? I mean, it's like graphs have existed way before computer science. And if we go back to the 6-year-old Nadia, like to me, that was just like, there's these so much mathematics that underline it, but it's also a core area in computer science as well.
So could you explain the bridge of Koningsberg, or I can find it on Wikipedia and like read the...
Hold on a second. Let me just, I'm going to pull it up here. I could explain it, but I just want to make sure I explain the right one. Yeah, it's traversing the bridges, right?
Yeah. I could just read the Wikipedia summary, I guess.
Yeah, it's probably better instead of me trying to repeat it.
Yeah, so the Wikipedia summary of the 7 bridges of Koningsberg is a historically notable problem in mathematics. Its negative resolution by Leonhard Euler in 1736 laid the foundations for graph theory and prefigured the idea of topology. So the city of Koningsberg in Prussia at the time was set on both sides of the Pregel River, which included 2 large islands that were interconnected to each other, or 2 mainland portions of the city by 7 bridges. The problem was to devise a walk through the city that would cross each of those bridges once and only once. By way of specifying the logical task unambiguously, solutions involving either reaching an island or mainland bank other than via one of the bridges, or accessing any bridge without crossing to its other end are unacceptable. Euler proved this problem has no solution. So that was in the 1700s. I saw there were a couple other examples. I don't know if any of them are of interest. Hamilton's Game or Zachary's Karate Club.
The Karate Club is the one that I think is was studied a ton before there was this explosion of social networks, right? People sort of studied the evolution of the club and the breakups of the club and all of those of the club. So yeah, there's been a bunch of them. I mean, and I think the difference is that, so even with the Euler, so even there, right, he's already looking at the combinatorics, right? So you're basically looking at all these combinations of these vertices and edges to try to understand if there's any way to traverse it. So when you're looking at the 7 bridges, that is tractable. You can do it. You can actually enumerate all the options with 7 bridges. I mean, why is this relevant, right? It's relevant because you want to sort of optimize construction of transportation networks, right? And as you start to look at increasingly more larger cities, larger bridge networks, larger road networks, it becomes increasingly more computationally expensive. And a lot of these problems, I mean, one of the things that's exciting and challenging about graph theory at the same time is a lot of these problems, they don't have polynomial time solutions. So they are in this combinatorial space, which I think why people like graph theory. It's computationally challenging. So you look for approximation algorithms, or you look to see if you can actually make progress on something that, see if you can find a polynomial solution, which is typically has been continuously proven to not exist or not found.
Could you explain what you mean by a polynomial time solution?
So maybe let's sort of come back. The other term that often comes up here is the NP complete, right? So if you are, for example, writing an algorithm, and say your algorithm operates on X number of data points, a polynomial time algorithm is going to take X squared time or X third time or X fourth time. In the context here, it's basically ends up being, whatever the combinatorial complexity is, right? So you don't have an algorithm that allows you to basically take an exponent of your number of data points.
Okay. So your dissertation was on graphs. Statistical signal processing for graphs is the title, I believe. And in that paper, you were using large-scale publication data sets to do some graph analysis. Could you explain sort of the background on that and what you found?
Sure. So I'd like to maybe start with some of the early motivation for this work. And this is interesting because a lot of this research and the work that I've done in graph theory, a lot of it started back at Lincoln Laboratory, right? And I was very much inspired by statistical signal processing theory of detecting things, right? So there's a very formal set of methods, to detect some sort of entity in context of a radar return. In graph theory, detecting patterns in graphs tends to be a lot more heuristic, especially large graphs. So a lot of motivation for my PhD dissertation and a lot of the research that preceded this was essentially, how do you create these techniques to be able to detect patterns? So be able to create distributions of signal and noise distributions for graph theoretic data sets. So essentially what I was curious, specifically for my dissertation, the problem that I looked for in my dissertation is there a detectable signature of emergence of a new academic field in a large publication data set?
Mm-hmm.
And work included both the development of techniques themselves and applying them to this publication data. So the techniques themselves are essentially look at things like, can you apply a filter? So if you know what a pattern looks like, can you apply it to a graph data set and pull it out? And then the application, and we actually worked with these, I believe it was World of Science data, publication data, to see if you can actually identify those signatures. I wrote my dissertation at ASU, so I was working with a number of interdisciplinary scholars who have studied history of science. And one of the things that's really hard in this space is truth data. So how do you know that a new field emerged, right? Like, I actually think in terms of interdisciplinarity, this is a really good example. Computer scientists often postulate that they have detected something in a data set, but it's not until you go to a historian, sociologist, or someone else that's a domain expert that they can actually validate that for you. So that was something exciting that I got to work with Manfred Labischler here at ASU. He is a historian of science, and he had some examples in evolutionary biology and other biology type of fields where new fields were merged. So I was able to test if my mathematical techniques were working.
Okay. So in your PowerPoint about your dissertation, there's a line that says, results confirm that innovation leads to rewiring of networks. Could you explain what that means?
Yeah. So if you think about, so let's start with the type of networks that you can construct from publication data. So say you have a bunch of publications, and one of the networks that is sort of the most natural to construct is co-authorships networks. So essentially you make all the authors vertices, those are your entities, and then you make the papers that they co-author together edges. So if you and I write a paper together, we're connected. If I also write a paper with Dan Lopresti, he and I would be connected. And you can build out networks out of that. So when fields are changing, those patterns are fundamentally changing. So say you and I are both computer scientists, and we are continuously publishing together. But if all of a sudden I start publishing with someone in supply chain, that is going to create different sets of connections. And those were some of the things that we were able to validate and be able to pull out of these large data sets when we did the analysis.
Okay. Has there been any further analysis of publication data throughout?
Oh, yeah. So I know for sure that Manfred has continued to graduate PhD students. So that it's in my dissertation, I've actually identified a number of future directions, and people have looked at it both from the perspective of techniques, and then people are also looking from a perspective of applying it to broader data sets. The other thing that I would say is generally this field is pretty active. So some of my colleagues at Lincoln Laboratory are still working in analysis of networks with these spectral graph theory techniques and matrix algebra techniques. So One of the people I will mention is Ben Miller. He's working on his PhD at Northeastern at their Network Science Institute. So there's certainly continuation of this work. And I do want to be very clear that this is, I've worked on this area probably for about 10 years or so. So there's a lot of things that Ben and I started at Lincoln Laboratory, and then we've had collaborations with Harvard and Patrick Wolf, and then at some point it was very cathartic to write up a lot of this work in a dissertation. So I think one of the things that I mentioned is I don't have an exactly traditional academic trajectory. And sometimes people look at it and say, oh, you did your PhD in 18 months. And I'm like, well, I did my PhD in 18 months, but I did a lot of research in the 10-year career before that. So I think that's really important to acknowledge.
So could you just kind of lay out your timeline? We maybe glossed over this in the beginning.
Okay.
As far as from when you went to undergrad until you got to ASU.
Sure. So as I mentioned, at about 6, I decided I was going to be a mathematician. I know you said undergrad, but we're going to go back to 6. So at 6, I decided I wanted to be a mathematician. At about 9th or 10th grade, I decided that was not necessarily a career that would allow me to pay off my future loans. So I decided to major in computer science. I wanted to go to a top CS program at the time, I remember. And as a high school senior, I was deciding between Cornell and Carnegie Mellon. And I just fell in love with Cornell on my visit. I have the best memories of my time there. So at Cornell, I was a computer science major. About a little bit into my computer science degree, I realized that I had quite a bit of AP classes that I took in my high school back in Ohio. And what I actually was thinking of doing was getting a double degree. I wanted to do a double degree in computer science, which would be a BS through the engineering school, and a math degree through College of Liberal Arts and Sciences. But when I went to talk to my undergrad advisor, they actually gave me some really good advice, which I don't remember this person, but that was probably really valuable. He basically said, look, why do you want to do the dual degree? You're already taking a ton of math in your computer science curriculum. Why don't you do a master's? You can do a master's in 4 years. So I finished my undergrad in about 3.5 years, and then I did a master's in just one more semester. So when I graduated from Cornell with a master's, I went to Lincoln Laboratory. At Lincoln Laboratory, I considered getting a PhD because I had always wanted to go get a PhD. But I was having so much fun, and I got to do research, and you do the PhD to do the research, and I was getting to do the research, but then also having impact. So I was publishing a ton, and I was doing very interesting research in a number of different areas. And eventually I got promoted to a level. I mean, I essentially broke the PhD ceiling at Lincoln Laboratory. So there wasn't really career motivation for a PhD. And I intellectually was very happy doing the work that I was doing. Then about in 2012, my husband, who is a professor here at ASU, decided that we should go to ASU. He didn't decide. We discussed it, obviously, but it was something that he really wanted to do because he wanted to be a professor. That's been his lifelong dream, and he had an opportunity to do it. He was a senior scientist at Lincoln as well. So we came to ASU, and once I came to ASU, I realized that in an academic environment, it's really helpful to have the PhD credential. And I actually had my advisor approach me, and he said, why? So Manfred, he said, why don't you have a PhD? Like, you have all these publications. Why don't you have a PhD? And I said, well, look, I did this stuff. That was the interesting thing. Like, do I really need this credential? And he's like, you should have a PhD. And I said, okay, can I get a PhD in 18 months? And I put out a plan because I'm a planner. I mapped it all out, and I said, if we can do it in 18 months and fulfill the requirements that are necessary, I will do it. Because at the time I was an assistant vice president, had a little kid and a husband pursuing tenure. So I was not willing to stop my job, and obviously I needed to spend time with my kid. So that's how I got my PhD. But it was great because I got to write up all that body of work I mean, a dissertation is it's a really nice thing to have. There's something very meaningful about it. And to be honest, like, it's a neat thing to show my daughter.
Mm-hmm.
Like, look, I could do this, and you could do this if you want to. You don't have to, but you could do this. So that's kind of the trajectory. And that was 5 years ago.
So do you think getting a PhD has made a difference in your life and career? Would you give people that might be in a similar position as you the same advice?
So I think it depends, right? It is, for me, I think there was a number of dimensions of it that were deeply meaningful for me. So I actually have a document that I wrote as a 9th grader that said that I was going to get a PhD. And not just a PhD, but a PhD in math. And my dissertation is actually in applied mathematics. So something about fulfilling that childhood thing was very meaningful, even though I wasn't necessarily planning to do that if I would have stayed in Boston. I will also say that there is a degree of credibility that comes with a PhD, which is helpful, particularly when you're working in kind of advanced R&D and S&T. So I think it very much depends on the type of career you're in. In the career that I am in, it absolutely, I would recommend it. But there's many other places where you don't need a PhD, and it certainly, many studies will tell you not to get it. I think the other thing that I would say from an advice perspective, what helped me is that I knew why I was doing it. It was very clear. It was sort of like I wanted to basically cohere this body of work. It was relevant to the position that I held in the university, and it was, to respond to that 9th grade Nadia. And on top of it, I had a list of things I wanted to do research on. I think it is a lot tougher if it's not so clear.
That's it for this episode of the podcast. We'll be back next week with part 2 of my interview with Dr. Nadya Bliss. In that episode, we discuss the work of Arizona State University's Global Security Initiative, how to combat the spread of misinformation, and the impact of sustainability on security. Till next week, peace.